Let's look at quadratic functions and finding their zeros using various techniques for how to solve quadratic equations. First, let's take a look at some definitions. A quadratic function is a function of the form f of x is equal to ax squared plus bx plus c, where the a, b, and c are going to be real numbers, and a is not allowed to be equal to 0, because if the a was 0, we wouldn't have the square term, and then we wouldn't be looking at a quadratic anymore. The domain of a quadratic function consists of all real numbers. Now, a quadratic equation is an equation of the form ax squared plus bx plus c is equal to 0, where a, b, and c are real numbers, and a is not equal to 0. Now, a zero of a function f of x is a number r such that f of r is equal to 0. Or, in other words, it's a number such that when you put it into the function, you get a 0 out. Perhaps in other words, we call a zero, we use this language that a value or a number is a 0. This is a solution to the equation when it's set equal to 0. So coming back up to our definitions of a quadratic function and a quadratic equation, we're seeing a lot of similarities, but what's going on is where this function output is, this f of x, we are going to instead insert a 0. So we're going to set our function equal to 0, we're going to make 0 the output, and then we're going to ask what are the inputs, what are the x values that generate that output of 0. Those x values are called the zeros, and sometimes you'll also hear them being called a root. So it'll be called a root of the function. Now in a little bit you're going to find out that the zeros or the roots are also referred to as the x-intercepts of the graph of the function. And we're going to look at why in just a moment. Alright, so what we're going to be doing then is we're going to be taking our function, we are going to be translating it into this kind of corresponding quadratic equation where it's going to be set equal to 0, and then we're going to solve this. So solving this equation will give us our zeros. There's going to be several different techniques that can be used to solve quadratic equations. So let's review some of the major techniques. Now you're going to need to be able to apply any of these techniques on demand, so they all need to be in your toolbox. We're going to be going over them very quickly with just some basic examples. If you want to see any more examples or like a more detailed tutorial, let me know and I can provide some additional resources for you. Alright, so the first major technique we're going to learn how to find zeros is by this technique of factoring. In example 1, we're going to find the zeros of f of x is equal to x squared plus 2x minus 15, and then we're going to list any x-intercepts of the graph of f. So when you're asked to find the zeros, that is asking us to find the x values such that the output is going to be 0. So in my function where I see f of x, I'm going to substitute in a 0. So I'll have 0 is equal to x squared plus 2x minus 15. And then I just need to solve this for the variable x by using the skill of factoring. Now factoring this, this is the easy case to factor. Because the leading coefficient, which is the number in front of your square term, is 1. So this boils down to looking at a product sum chart. Now you might have other techniques that you have picked up along the way about how to factor these. You don't have to factor using what I'm about to show you, but I just want to remind you of a technique just in case it's been a while since you've seen how to factor these. All right, so we're looking for two numbers whose product is -15 and whose sum is 2. Now, if this factors, it will only factor in one way. Now, the product of -15 is going to be a finite list. So sometimes when you're having problems finding the pair to factor, it's just helpful to write them all out. So the 15 can either be formed by doing 1 times 15 or 3 times 5. And that's it. That's the only way to multiply two numbers to get a 15 out. Now, specifically, I'm trying to build a -15 and a +2, and I can see I can do that with the 5 and the 3 as long as the 5 is positive and the 3 is negative. All right, so those are going to be the two numbers that I need to complete my factoring. So I'm going to come back over here in the problem. So this thing will factor into x minus 3 times x plus 5. Or you could have written it as x plus 5 times x minus 3. The order that you write the factors does not matter. So as a reminder, we call these the factors of this polynomial, this x squared plus 2x minus 15. Okay, so just a little bit more vocab that you should be comfortable with. It absolutely matters that the 5 gets the positive and the 3 gets the negative, so pay attention to your signs. All right, so now we're going to use what is called the zero product property. All right, so the zero product property says when you're multiplying some stuff and the product is 0, then one of the factors actually has to be equal to 0. So we're going to use that. So we're going to set each one of these factors equal to 0. So if the x minus 3 is equal to 0, that means x is equal to 3. And if the x plus 5 is the factor that's equal to 0, that means x is equal to -5. All right, and we are done. These values right here, this x equals 3 and this x equals -5, these are my zeros. These are the values such that when I plug them into the original equation, it makes the function output a 0. So let's actually see that. So as an example to show you why we call x equal 3 a 0, in my function, if I put 3 in, I'll have 3 squared plus 2 times 3 minus 15. So 9 plus 6 minus 15. 15 minus 15. I get a 0 out. Now this actually then also ties into an ordered pair. I input 3 in my function and I got a 0 out. We can write that input-output relationship as an ordered pair. The ordered pair would be 3, 0. So then to go to the last part of this question, list any x-intercepts of the graph. The x-intercepts are going to be the ordered pairs 3, 0 and -5, 0. Or we can shorten how we say that, and we can say the x-intercepts are 3 and -5. This version of the language, just giving the x-intercepts as numbers, this is a more advanced way of talking about x-intercepts because, and sometimes dangerously so, you assume your reader knows these are ordered pairs. And specifically as an ordered pair, I'm giving you the x-coordinate and its corresponding y-coordinate is 0. Sometimes I've seen students think that this as an ordered pair forms the ordered pair like 3 and -5 or something like that. So when I say the x-intercepts are 3 and -5, more specifically the x-intercepts are the ordered pairs 3, 0 and the ordered pair -5, 0. So that's why I just like sometimes talking about the x-intercepts as ordered pairs and not just giving that one number, because in math it's sometimes not good to assume that your reader understands some of those intricacies in the language. So we're seeing kind of a cool little property come out of all of this. If R is a zero of the function, then R is an x-intercept of the graph of f. All right, so this idea about zeros and intercepts, they're the same. Makes it real easy to answer that intercept question. All right, let's take a look at another example. For example 2, it says find the zeros of f of x is equal to x squared minus 8x plus 16, and then list any x-intercepts of the graph of f. All right, so again, when I ask you to find the zeros where the f of x is, we're going to put a 0 in. And then the question is, what are going to be the x values here such that I get that 0 is my output, and we are going to answer this using the skill of factoring. So again, this is the easy case because the leading coefficient is a 1. Okay, so the x squared will factor into x times x. And then to fill in the second blanks, we need two numbers who multiply to positive 16 but add to negative 8. Negative 4 and negative 4, you say? All right, so we're going to put those in the second blanks. All right, so then we're going to set the factors then equal to 0. In this case, my factors are the same. It's the same factor, so I don't have to set both of them equal to 0. I just need to do one. So x minus 4 is equal to 0, so that means x is equal to 4. All right, so this is our 0. So for this particular example, we have one real 0. And sometimes we refer to it as a 0 of multiplicity 2. Because this 0 occurs twice because of the two factors. Sometimes another thing that we would say is we call this a repeated root, because the solutions to these equations are also referred to as roots. All right, so now we're seeing that we could have zeros or roots with multiplicities. Okay, so let's take a look at one last example using the skill of factoring. So for example 3, we're going to find the zeros of f of x is equal to 6x squared plus 13x minus 5, and list any x-intercepts of the graph of f. And I'm looking at that listing any x-intercepts, and I'm thinking we didn't do that back on this one. So let's go ahead and finish that. So listing x-intercepts of the graph of f. You could say the x-intercept is 4, or you could be a little bit more careful and you could say the x-intercept is 4, 0, and actually give it as an ordered pair. I don't mind either way. I think the ordered pair is a little bit more clearer to everybody, but just giving the x values is more advanced and a little fancier. All right, okay, so coming back up to this one. Find the zeros of the 6x squared plus 13x minus 5. So this case, again, to find the zeros where the f of x is, you're going to put a 0 in, and we want to solve this resulting equation. And again, as a reminder, we want to use this skill of factoring. Now, this one is the harder case to factor, because that leading coefficient of that squared term is not equal to 1. Now again, you might already have some techniques that you know how to factor this, but I'm going to talk about two major techniques. One of them is sometimes called unfoil, or I've heard it called just guess and check. And the other major technique is, I refer to it as the AC method. All right, so let's review what those two techniques are. I think it's helpful to actually have both of them because some problems are going to be easier to use the guess and check method, or the unfoil method, and other problems are going to be easier to use the AC method. All right, so let's first do the unfoil. All right, so I've got my 0 is equal to 6x squared plus 13x minus 5. All right, so in this case, we are going to look at how do I build that 6x squared, and then how do I build that negative 5. So for the 6 part of it, I could either be 1 and 6 or 2 and 3. For the negative 5 part of it, or just the 5 is really what I'm paying attention to right now, it's going to be the 1 and the 5. So what I'm going to do is I'm going to put down 2 sets of blanks, and I'm going to start picking numbers from the 6 factors to put in the front spots, and then numbers from the 5 factors to put in the second spots. Now the unfoil method really shines when you have values that are going to be prime. All right, so we like the primes when we're doing this because it limits the amount of options that we're going to have if this thing is going to factor. So I don't really have any choices. In the second spots, I have to have the 1 and 5. So then I need to pick which numbers are going to be in the front spots. The 1 and the value is usually the extreme case. I usually test that one last. So I'm going to try the 2 and the 3. But you have to be very careful about where you put the 2 and where you put the 3 because it's going to affect your inner and outer factors. So keep in mind you're trying to build a 13. So I'm looking at my 2 and my 3 and I'm thinking, okay, well if I put my 3 here in the first spot and I put my 2 here in the second spot. Now I also need to build that x squared, so I'll need x's on both of those. Okay, but the x's that's the easy part. It's figuring out the numbers that makes this a little bit more difficult. What's going to go on here is my inner term is going to be 1 times 2x, which is 2x. My outer term is 3x times 5, which is 15x. And I can put a 2x and a 15x together to form my positive 13x if the 15 is positive and the 2 is negative. Which means then, if I want the 15x to be positive, I'm going to need a plus in front of the 5. And if I want my 2x to be negative, that means I'll have to have a negative in front of the 1. Now notice that does work out for the sign that I want my last term to be. I wanted that last term to be a negative. And a negative times a positive does give me a negative. So all my signs work out, all my numbers work out, life is good. So that's how this thing will factor. All right? But I needed to check my inner and outer products to make sure that my placement was correct. So then we're just going to finish solving this. So if the 3x minus 1 is the factor that's equal to the 0, that means x is equal to 1/3. If the 2x plus 5 is the factor that's equal to 0, that means x is equal to negative 5/2. Okay, so these are my zeros, which means that they're also my x-intercepts. All right, so maybe I'll explicitly list this up here too, so I don't forget that the x-intercepts of this problem are 1/3 and negative 5/2, or if you wanted to be a little bit more clear, you could write the ordered pair 1/3, 0, and the ordered pair negative 5/2, 0. All right, so please just leave those as fractions. No need to convert any of that stuff to decimals. All right, so that was unfoil. Let's review what the AC method is. Now when I'm looking at this, so generally this is written as ax squared plus bx plus c, right? So we need that because it's going to tell me what my a is and what my c is. Now what's going to go on for the AC method is that you are going to make a product sum chart, kind of like we did on that first example, but my product is going to be what I get when I multiply a times c, and my sum is what that b value is. All right, so for my product sum chart then, let me move that down. So I'm going to be doing 6 times negative 5, which is negative 30, and my sum I want to be positive 13. All right, so let's go through and write down all the different ways I can build a negative 30. So it could be 1 and 30, 2 and 15, 3 and 10, 4 doesn't go into 30, 5 and 6, and now I've listed them all. So you're going to be looking at those numbers and then trying to find out which pair of numbers hits that product but also meets that sum. Now, be very careful. Now you might be tempted to look at it that 3 and 10, be like, oh, if I put a 3 and 10 together, I get the positive 13 out. But we got a problem. We're trying to build a negative 30 for our product. So we really do need to be careful for signs. The only way the 3 and the 10 end up being a positive 13 for the sum is if the 3 is positive and the 10 is positive. But a positive times a positive does not get me my negative product. So that 3 and that 10 looks very tempting, but it's not going to work. The pair that's going to work for us is going to be the 2 and the 15. That will get me my negative 30 for my product and my positive 13 for my sum, as long as the 15 is positive and the 2 is negative. Now here's the catch on the AC method. You can't go directly to your factored form like we did on that previous example. What's going to happen now, once I find the two numbers that work, is we are going to take our original polynomial and we are going to expand out this middle term using our two numbers that we just found. So what that's going to look like is 6x squared and then minus 2x plus 15x minus 5. All right, so I've actually took the polynomial and I made it longer. Now that might also then mean more complicated, right? But the key thing right now is we are going to factor this by using a technique called factor by grouping. So let's just quickly review what you need to do to factor by grouping. So we're going to group our polynomial. Now notice you have 4 terms. That's really important in factor by grouping. You got to have 4 terms. We're going to group the terms 2 by 2. Now as opposed to introducing parentheses, I just like to do my underlining so I can visually see my groups. In each group you're going to factor out its GCF. So in the first group, the 6x squared minus 2x, its GCF is 2x, so if I factor that out, I'll be left with 3x minus 1, and then close the parentheses because I'm finishing factoring that group. And then looking at my second group, its GCF is positive 5, so I'm going to pull out a plus 5, and if I pull that off of the two terms, I'll be left with 3x minus 1. Cool. And this is what you want to have happen. You want this common binomial to pop out on each one of these expressions that you factored. So then you're going to factor that out, 3x minus 1. And if I pull it off of my two terms, I'll be left with 2x plus 5. And then it's set equal to 0, and there you have your factored form. And then we would just finish this the exact same way we did on the unfoil method. So the AC method is a little bit more complicated. There's a little bit more going on involved because you've got this factor by grouping technique, but the AC method really shines if you have a polynomial that has a lot of factors that you would have to check using the unfoil technique, or if you think that the polynomial is prime, again it can't be factored, but you're not 100% certain, the AC method will tell you, because if you make this product sum chart and you can't find two numbers that hit your desired AC product, that also will hit your target sum, then you know that the polynomial is prime and you're going to have to solve the quadratic using other techniques. So that kind of goes over the techniques for factoring, but not all polynomials can be factored. So if the polynomial can't be factored, how else can we solve that quadratic? Well, let's get into some other techniques. So the next one that we are going to look at, the next major technique that you need to have mastered, is called the square root method. And you've actually already seen this a little bit. We used this a lot when we were doing the circle stuff earlier in the course. The short condensed version of the square root method is that it just says that to undo squaring, you square root. But we have to be a little bit careful when we introduce that square root. So if I have x squared is equal to p, so we'll undo this squaring with a square root. But if we introduce the square root and we square root both sides, on the side opposite your variable you'll have a plus or minus. We have to account for the principal root or the positive value that would make this equation true, and we'd have to account for the negative root. And just as a side note, when I use this word root here, that's different than the use of the word root that we were talking about previously when we were talking about zeros. Okay, so this root is a short version of talking about general radicals, so square roots, cube roots, things like that. Whereas the root before, we were talking about solutions to equations. So I know, that's vocab for you. So when you introduce the square root, you have to introduce the plus or minus on the side opposite your variable to account for the principal root and the negative root. Now on this side with the variable, the square and the square root cancel, and you'll just get the radicand, in this case that x, that'll fall out. And on the other side you get plus or minus the square root of p. So maybe as a more concrete example, so we can kind of see what's going on here. Let's say that my equation was x squared is equal to 9. So this is asking you what number, such that if I square it, do I get 9 out? Well, just by using our math facts, we can say that 3 squared is 9, but also negative 3 squared is 9, because negative 3 times negative 3 is equal to positive 9. So using this square root method, if I wanted to solve for this variable and I square root both sides, don't forget about your plus or minus as soon as you introduce your square root. So on this side, the square and the square root cancel, and I just get x. And on this other side, I get plus or minus the square root of 9. And then we know that we can simplify the square root of 9 to 3. So there is your principal root, the positive 3, and then the negative root, which would be negative 3. Alright, so then the definition of the square root method is if x squared is equal to p, and that value for p is greater than or equal to 0, then x is equal to the square root of p, which is your principal root, or x is equal to the negative square root of p, which is your negative root. Now for this condition right here, we require that value for p to be greater than or equal to 0, because if p was less than 0, the number on the opposite of your square was a negative number, you're going to get a complex number. Okay, so it's going to involve that imaginary unit I. And at that point in time, you're not working just inside the real number system, you're working in the complex number system, of which the real number system is a subset. That's something that will be explored further later, but just for right now, we're working in our real number system, so this number over here is always going to be positive or 0. So let's take a look at a couple of examples applying this square root method. And now again, whatever method you're told to use, you should need to use that method to solve the problem, not a different method. So for this next example, it says find the zeros of each function and list any x-intercepts of the graph. My first example is going to be f of x is equal to x squared minus 7. Now I want you to notice that there's no linear term on here, there's no x to the first power. Okay, so those are going to be really good candidates to use that square root method to solve the quadratic equation. So again, to find the zeros, where the f of x is, you're going to put a 0 in. So I get 0 is equal to x squared minus 7. Let's isolate that squared term, so I'm going to add 7 to both sides. Now to undo my square on my variable, I'm going to square root. And now again, when I introduce the square root, don't forget about the plus or the minus on the side opposite your variable. So I get plus or minus the square root of 7 is equal to x. The square root of 7 doesn't simplify, so I can go ahead and leave it like that. So these are going to be my zeros. And then my x-intercepts. In shorthand notation, you can say the x-intercepts are the square root of 7 and negative square root of 7. Or if you wanted to write them as ordered pairs, you could do that as well. One more example using the square root method. The next function is g of x is equal to the quantity of x minus 4 squared minus 9. So to find the zeros, again I'm going to let 0 equal my function output. So I'm going to get 0 is equal to the quantity of x minus 4 squared minus 9. We're going to isolate this squared term by adding 9 to both sides. And in this case, there is no need to multiply this piece out. Right? I'm going to be able to undo this squared by square rooting, because it's kind of this entire quantity right here that's being squared. So I'm going to introduce the square root on both sides. Again, don't forget about your plus or minus. So on this side, you get plus or minus the square root of 9, which is 3, is equal to, and on this side, the square and the square root cancel, and this radicand, which is x minus 4, just drops out. So then to solve for my variable, I'm going to add 4 to both sides. Now I tend to make a lot of goofy arithmetic errors here because of this plus or minus notation. So at this point in time, I like to actually record the two cases I'm looking at so I can more easily see what's going on here. So in one case I'll have 4 plus 3, which is 7, and in the other case I'll have 4 minus 3, which is 1. The arithmetic is not complicated, but I tend to make a lot of really goofy sign errors here, so I just gonna clearly write out what's happening. So these values, 7 and 1, are my zeros. So then the x-intercepts for this function are 7 and 1. And again, as ordered pairs, that would be 7, 0, and 1, 0. So that was the square root method. The next method that we're going to look at is solving these by completing the square. So in this next example, it says find the zeros of f of x is equal to x squared plus 6x plus 5 by completing the square. List any x-intercepts of the graph. So to start off with, the idea about finding zeros is where your function output is. So you're going to put a 0, and then we're going to find these values for x that would make this true. So for the process of completing the square, let's review how to do that. So the first thing is you're going to move your constant to the other side. So you just have your squared term and your linear term on the one side. So in this problem, I would get negative 5 is equal to x squared plus 6x. Right, so now the next thing is you're going to, and this is kind of the special step here, is you're going to take the coefficient of your linear term, multiply by 1/2, or divide by 2, however you want to think about it, and then square it. You're going to add that result to both sides. And so that's your next step. So this is where it's sometimes helpful to put a blank to remind yourself on what you're going to add to both sides. And this step is so special that I don't just do it in my head. I take a moment to record it as part of my work as like a step that I can remind myself about where I'm getting this number. So I'm going to take this 6 divided by 2 and square it. So that'll give me 3 squared, which is 9. This is the number I'm going to add to both sides of my equation. Right, so let's clean up what we have on both sides. On the left-hand side, I'll have 9 plus negative 5, which is 4. And then over here, this is a perfect square trinomial, so this will factor into x plus 3 squared. Right, so now that I have this term, I can go back to my square root property to finish this out. Right, so we'll undo the square with square root. Don't forget about the plus or minus. Right, so I'll get plus or minus 2 is equal to x plus 3. Solve for my variable by subtracting 3 from both sides. And then again over here on this left-hand side, I'll have negative 3 plus 2, which is negative 1, or negative 3 minus 2, which is negative 5. So these two values, negative 1 and negative 5, are my zeros. And then just as a side comment, because these zeros are nice integers, this original problem could have actually been solved by factoring as well. So the x-intercepts for this function are negative 1 and negative 5, or as ordered pair, negative 1, 0, and negative 5, 0. Now, as a word of caution about the completing the square process, if the coefficient of the squared term is not a 1, you're going to need to divide through by that coefficient of that squared term before you do the completing the square process. So let's see an example of what that means. So let's say we were asked to find the zeros of g of x is equal to 2x squared minus 8x minus 5 by completing the square. And then again, we're going to list any x-intercepts. Well, because I'm asked to find the zeros of this function, I'm going to put 0 in for my function output, g of x, so I'll have 0 is equal to 2x squared minus 8x minus 5. Now, I was told to use completing the square as the process. So in order to complete the square for this squared term, it has a coefficient of other than 1. So I'm going to need to divide everybody by that coefficient of 2. Right, so we'll get 0 is equal to x squared minus 4x minus 5 halves. Okay, so now I'm in the good position to complete the square on this. So the first thing I'm going to do is I'm going to move this constant to the other side. Okay, so I'll have 5 halves is equal to x squared minus 4x. At this point in time, I'm going to want to add something to both sides. I want to take the coefficient of my linear term, which is negative 4, divide that by 2 and square it. So I'll get negative 2 squared, which is 4. So 4 is what I'm going to want to add to both sides. Over here on this left-hand side, let's see, 4 plus 5 halves. 4 is equivalent to 8 halves. So I'll have 8 halves plus 5 halves, which is 13 halves, is equal to, and this other side will factor into whatever this number is right here before you squared it. So it'll factor into x minus 2 squared. Right, so now I can undo my square with square rooting both sides. Over here on the left-hand side, I'll get plus or minus the square root of 13 over the square root of 2, which I can go ahead and just rationalize that right now, multiply both sides by the square root of 2. And then on this side right here, I'll get x minus 2. So we're going to need to add 2 to both sides. So I'll have 2 plus or minus the square root of 26 over 2. So that's going to be equal to my variable, or if you wanted to, you could common denominators here and push all this together. That would be 4 plus or minus the square root of 26 all over 2. That's another way that you could write your final answer. Alright, so these are going to be my zeros, and my x-intercepts would be 2 plus the square root of 26 over 2, and 2 minus the square root of 26 over 2. So this one, we just had to be a little bit careful right here, right, in terms of completing the square. Because the leading coefficient of my squared term was not a 1, I needed to divide everybody by that coefficient and make it a 1 before I could do my completing the square process. Alright, so there is the completing the square process. The next process we're going to look at to solve our quadratic equations is going to be the ever famous quadratic formula. Alright, so given your quadratic equation ax squared plus bx plus c is equal to 0, where a is not equal to 0, if b squared minus 4ac is less than 0, so this b, this a, and the c come from the coefficients of your quadratic equation, if that computation is less than 0, then this equation has no real solutions. If b squared minus 4ac is greater than or equal to 0, the real solution or solutions of this equation are given by the quadratic formula. Quadratic formula is that your variable, in this case x, is equal to negative b plus or minus the square root of b squared minus 4ac. All of that is over the quantity 2 times a. It is important that you memorize this. This is definitely something that you need to have in your toolbox. You can go on YouTube and you can find all sorts of people singing it or doing weird things with it to try to help them memorize this formula. So I encourage you to take advantage of that. Try to find someone who's put this to a song. This part right here, this b squared minus 4ac that's being talked about up here, that is called the discriminant. Based upon what's going on with the discriminant, we can tell what's going to happen with the solutions to our quadratic equation. So as we had mentioned before, if b squared minus 4ac is less than 0, then there is no real solutions. Okay, so therefore the graph of the function will have no x-intercepts. Now, if your discriminant b squared minus 4ac is equal to 0, then there's going to be a repeated root, a repeated real solution. So your root is going to have multiplicity 2. So in your graph will have one x-intercept, and if b squared minus 4ac, your discriminant, is greater than 0, then there's going to be two unequal real solutions. What's going on with the discriminant and what that tells you about your solutions and your x-intercepts? This is important to know, so you should memorize these cases. For the b squared minus 4ac is greater than 0, for it being positive, there's actually something else here that I find that's helpful to remember. If b squared minus 4ac is a perfect square, then you're going to have two rational solutions. So remember, rational numbers can be expressed as a fraction. And just as a side note, then that meant the original equation also could have been factored. If b squared minus 4ac is not a perfect square, then you're going to have two irrational solutions, which means that the solutions will involve a square root of some sort. So I like to know that because it tells me just by looking at it whether or not it's a perfect square or not, if I'm going to have to deal with radicals in my final answer. Let's take a look at a couple examples of applying that quadratic formula. So find the real zeros if any of f of x is equal to 2x squared minus 4x plus 1. List any x-intercepts of the graph. Right, so since I'm being asked to find the zeros where the function output is, I'm going to put a 0. So I'll have 0 is equal to 2x squared minus 4x plus 1. In order to use the quadratic formula, let's identify our a, b, and c. So our a is 2, our b is negative 4, and our c is 1. Anytime that you're trying to memorize a formula, it's strongly encouraged, especially when you're working through your homework, start your work writing the formula you were trying to remember. Right? It just starts repeating it over and over again to help you memorize it. So our quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's start substituting in our values. So the negative is part of the formula. My value for b is negative 4. I'll clean up that sign on my next step. Plus or minus the square root of negative 4 squared. Do not forget about those parentheses. They are not optional. Minus 4 times my a value, which is 2, times my c value, which is 1. Make sure your radical bars are long enough to capture everything that you want underneath them. Make sure this fraction bar is long enough to capture all of that in your numerator. And then in my denominator, I'll have 2 times 2. Now we just clean this up. So I'm going to have 4 plus or minus the square root of, this is going to be 16 minus 8 underneath the square root, all over 4. So 4 plus or minus the square root of 8 over 4. For the square root of 8, I can factor out or pull out the square root of 4, which is 2. It'll leave me a 2 trapped, so I'll have 4 plus or minus 2 root 2 over 4. And then this can be simplified two different ways of thinking about it. If you can find a number that goes in here, here, in here, so kind of like this triangle, you can divide it out. So 2 goes into all of those, so 2 divided by 2 is 1. 4 divided by 2 is 2, 4 divided by 2 is 2. So then that would simplify to 2 plus or minus square root of 2 over 2. Another way you can think about it, simplifying this, is break this into two separate fractions. 4 over 4 plus or minus 2 root 2 over 4. That would simplify then to 1 plus or minus root 2 over 2. Okay, so wrapping up what we have so far, my x-intercepts are going to be, or my zeros rather, doesn't matter because they're both the same. So let's maybe talk about this in terms of my zeros first. So my zeros are 1 plus square root of 2 over 2 and 1 minus square root of 2 over 2. Now, those are also going to be my x-intercepts. And if I wanted to, I could write those as ordered pairs. 1 plus square root of 2 over 2, 0, and 1 minus square root of 2 over 2, 0. So apparently I'm going to have two x-intercepts of my graph. Let's go verify that. Let's actually take a look at the graph of this and see what's going on. So I'm going to use Desmos for graphing. All right, so if you're not familiar with Desmos, you can just go to desmos.com and then open up their graphing calculator. So I'm going to go ahead and put in my function. So 2x squared minus 4x plus 1. And then taking a look at this, and maybe let's zoom in on this graph, we can see that yes, indeed, this graph does intersect the x-axis twice. And if I wanted to find out the location for those x-intercepts in Desmos, what I would do is I would just click on the point. And it's going to predict what I'm trying to find. There are very common features in math that we look for graphs. So for one of these x-intercepts, the lesser one, apparently the out to 3 decimal places, is going to be 0.293. So going back here, this is going to be the lesser x-intercept of the two, so I'm going to assume that's my 0.293 is my approximation. And then the other x-intercept over here would be 1.707. Now if I ask you for the x-intercepts, I don't want the approximation, I want the exact answer, but the approximation is very handy for the graphing purposes. So while Desmos will tell you the decimal approximation for those x-intercepts, if you're asked for the x-intercepts of this graph, like we were up here, you're going to want exact answers. So you're not going to be able to get that from the graph. You're going to get that from actually solving this quadratic equation. And we use the quadratic formula. All right, one more example using the quadratic formula. So let's find the zeros, if any, of f of x is equal to 4x squared minus 2x plus 1, and again, we're going to list any x-intercepts of the graph. So finding zeros, I'll plug 0 in for my output, so 0 is equal to 4x squared minus 2x plus 1. My a is going to be 4, my b is negative 2, and my c is 1. So putting that in my quadratic formula, I'll get x is equal to negative 2 plus or minus the square root of negative 2 squared minus 4 times my a, which is 4, times my c, which is 1, all over 2 times 4. So we'll start cleaning that up. So x is equal to 2 plus or minus the square root of 4 minus 16 all over 8. And here's where I start seeing something a little fishy happening. 4 minus 16 is negative 12. All right, so I can stop right there. This value, this negative 12, this is my discriminant. So I have a discriminant that is negative. Okay, so I can stop immediately right here. There are no real zeros, and there are no x-intercepts of this graph. You could graph this yourself to verify that, but here's the power of just looking at the discriminant and knowing what that tells you about your solutions. So this one will not have any real zeros. It's going to have complex zeros, which we'll talk about later. All right, so moving on. Finding the points of intersection of two functions. So in this next example, if f of x is equal to x squared plus 2x minus 1, and g of x is equal to 3x plus 1, okay, so you can see one of them is going to be a quadratic equation or quadratic function, and the other one is going to be a line, a linear function. Solve f of x is equal to g of x. At what point or points do the graphs of the two functions intersect? Now what we're looking for here is the points x, y, so we're looking for ordered pairs x, y that are on both graphs. Right, so that's what's going on here. So this is saying we want to find the value for x, and it's the same value of x for both equations, right? That x is going to be equivalent to that x. So we want to find x such that the y values, right, the outputs, are equal. Now we could graph this to find those points, but a couple of problems. One is most of the time we want you to find these solutions algebraically and actually use all of your algebra skills. But the other problem is a lot of the times these intersection points are not going to sometimes be very nice integers or things that you can read off easily. So if you graph it, you can see that yes, there are in fact intersection points, but it's not really great at telling you what they are or giving you an exact answer. You might get a decimal approximation, which is sometimes okay, but other times not so much. So let's actually solve this. So we're going to take their hint, and we are going to let f of x is equal to g of x, and we're going to solve that. So f of x is equivalent to x squared plus 2x minus 1, and g of x is equivalent to 3x plus 1. So I need to solve that. This is going to be a quadratic, so let's get one side equal to 0. So I'm going to move all these terms to the other side. So I get x squared minus x minus 2 is equal to 0. Now for this quadratic that I have right here, you could solve this using any method. So, you know, completing the square is usually not most people's first choice. It might be for you. But it's a little bit more involved. If you wanted to, you could use the quadratic formula, but don't overlook factoring. If you can identify something that factors, that's usually a very, very fast way of breaking this down. The leading coefficient is a 1, so this is the easy case to factor. Can we come up with two numbers that multiply to -2 but add to -1? Well, 2 and 1 work as long as the 2 is negative and the 1 is positive. Now, not everything factors, but if it does, that's an easy way to break this down. So we'll set each factor equal to 0. If x minus 2 is equal to 0, that means x is equal to 2. If x plus 1 is equal to 0, that means x is equal to -1. Now, what we just found here is that these values are the x coordinates of my intersection points. Okay, so if I think about, I'm finding ordered pairs, right? I just found the x coordinates. So apparently one of the intersection points is going to happen at an x coordinate of 2, and the other intersection is going to have at an x coordinate of -1. Now I have the x coordinates. That's not enough. We now need to find the y coordinates. So in order to find the y, we are going to back substitute these x values into one of our previous equations, and you could either use f of x or g of x. It doesn't matter because the point is going to be on both graphs, so use whatever function you think would be easier. I think in this particular problem my g of x function was a little bit easier, so as a reminder, g of x is equal to 3x plus 1. So I'm going to first find g of 2, so 3 times 2 plus 1, which is going to be 7. So that'll complete this ordered pair. So if an x coordinate of 2, my y coordinate is going to be 7. And then I need to find g of -1, which is going to be 3 times -1 plus 1, which is -3 plus 1, or -2. And then that will complete my second ordered pair. So apparently I'm going to have these two very nice integer coordinates for the intersection points of these graphs. Maybe let's verify that we're seeing this in Desmos. So again, I'm going to come back to Desmos. Let's get our other equation out of here. So I have x squared plus 2x minus 1 as one of my functions, and the other function is 3x plus 1. So let's go ahead and I can use this to zoom out so I can see, yep, I'm definitely going to have 2 points where these two graphs hit each other. And if I just click on it, it'll tell me what the points are. So here I can see that 2, 7 is going to be one of the intersection points. And if I slide down here, here is your -1, -2. Okay. So the last thing that we are going to look at is, if we haven't done enough in this section, is to look at problems that are quadratic in form. All right, so they're not necessarily going to be a true quadratic, but they're going to behave like your quadratic equation. And now, as a reminder, your general quadratic equation is going to be ax squared plus bx plus c is equal to 0. So specifically, you have a squared term, and then a linear term, and then a constant. So that's going to be your general prototype for your quadratics. Now, these are quadratic in form. So let's take a look at this first example. Find the real zeros of the function f of x is equal to x minus 3 quantity squared plus 5 times the quantity x minus 3 minus 6. And then again, find any x-intercepts of the graph. Now, at this point in time, you could multiply out all of these pieces, collect like terms, reform your quadratic, and then go from there. Except that's spending a lot of time when you don't need to, and why would we spend more time if we don't have to, right? The important thing on this one is to recognize that they repeated the x minus 3 factor. I see that in both spots. That is going to be very special on here. So we're going to use that to analyze this from a quadratic in form sort of idea. So here's what we're going to do. We are going to, well, first off, because I want to find a 0, for my function, I'm going to put a 0 in, right, for my output. Right, so I'll have a 0 as my output. Now, what we're going to do is we are going to assign a temporary variable. We are going to let u equal that repeated chunk of information, that x minus 3. Now, u is the most common variable that we use here. It's usually referred to as a u substitution. You might as well get used to it now, because in calculus, u's and v's are what's going to be used for substitution variables. But this is a very common technique that we take something that looks complicated and we instead write it into something that we feel more comfortable and that we know how to solve. Now, letting u equal this x minus 3 chunk, what that means is everywhere I see the x minus 3 chunk, as opposed to writing it again, I can write now a u. So my equation would look like this. 0 is equal to u squared plus 5u minus 6. And that looks very similar to the original problem, but a lot easier to solve. And here's where we get this idea about it being quadratic-like in form. Now you might be like, but wait, I thought we were supposed to tell you what the value for x is in the original equation. Now you're going to have u. We'll get there, all right? We'll deal with that at the end. We'll circle back and we'll make everything come together real nice. Now, this new equation, 0 is equal to u squared plus 5u minus 6. Let's go ahead and solve that quadratic. You can use any of the techniques you want. I think this is going to be perfect for factoring because I can easily think of two numbers that multiply to -6 but add to +5 are going to be +6 and -1. Okay, so this thing will then factor into u plus 6 and u minus 1. We'll set each factor equal to 0. So if u plus 6 is equal to 0, u is equal to -6. If u minus 1 is equal to 0, then u is equal to 1. Now here's where we're going to circle back, right? I didn't ask you what u was. I want to know what x was, right? Well, we want x. We don't want u. But hey, I have a rule that tells me how to go back and forth between the two variables. This rule, don't just do it in your head. Write it in your notes so that not only you, but other people looking at your work know how you're swapping out pieces. So everywhere I see u, I'm now going to rewrite the x minus 3 piece. So I'll have x minus 3 is equal to -6. For one of the equations I need to solve, and x minus 3 is equal to 1 for the other equation I need to solve. All right, so let's solve those. Add 3 to both sides. I get x is equal to -3 or x is equal to 4. These are my zeros. And then the x-intercepts of the graph are going to be -3 and 4. So you could write it just by giving them, or again, you could list them as an ordered pair. All right, so kind of a cool technique, being able to use this substitution to break something down into something that's easier and that I know how to solve. Let's take a look at another example using that substitution idea. For this example, it says find the real zeros of the function g of x is equal to x plus 2 times the square root of x minus 3, and then again find any x-intercepts of the graph. Now again, to find the zeros for the function output, I'm going to put a 0 in. And if you wanted to, you could pull out, from your toolbox, how do you solve things with radicals in them and things like that. But the key thing in this one is this thing is quadratic-like. It's not a true quadratic, right, because there's no x squared term, but it's quadratic-like. So remember, quadratic-like is that you're going to have a squared term and then a linear term, and then you might have a constant. Now, this might not necessarily at this point in time look like that, but if we let u equal the square root of x, then u squared is equal to the square root of x squared, right? I'll just square both sides, and on this side the square and the square root cancel, and I just get x out. So here's where I have my base variable. I'm going to substitute that in for x, and then this other piece right here is the square of that. Right? So u squared, it would then go in right here. So what this is going to look like then, if I do my substitution with my temporary variable, where I see x, I'm going to write u squared plus 2, and now as opposed to writing square root of x, I'm going to write u, and then minus 3. And there's where you get that quadratic-like structure. This term was the square of this kind of middle term right here. Now again, you could use whatever technique you wanted to solve for this, but this thing will also still factor very nicely. Two numbers who multiply to -3 but add to +2 is +3 and -1. So this will factor into u plus 3 times u minus 1 is equal to 0. Now we'll set each factor equal to 0. So if u plus 3 is equal to 0, u is equal to -3. If u minus 1 is equal to 0, that means u is equal to 1. Now again, we're going to use our rule that we came up with up here, and we're going to back substitute it so that my final answers are not in terms of u, but they are in terms of x. So u is equivalent to the square root of x. So as opposed to writing u right here, I'm going to write the square root of x. And as opposed to writing u over here, I'm going to write the square root of x. So I have the square root of x is equal to -3, and the square root of x is equal to 1. Now I would just need to solve those equations. Looking at this first one, the square root of x is equal to -3, well, that's a problem, right? You can't take the square root of a number and get a negative out. Okay, so this is not a real solution. Right, now at this point in time, we're only going to be working for real zeros, right? I was told to find real zeros. So this part is going to be not real, so this is going to generate for me anything that's useful. But the other side is, so to get rid of that square root, I'm going to square both sides. So I would get x is equal to 1. So at this point in time, then I only have a 0 of 1 and an x-intercept of 1. Or if you want to write that as an ordered pair, 1, 0. So this problem then only had one real zero.